Oh, you fixed it, Rachel.
Yeah. I looked at it and I did something with standard deviation, I guess.
Yeah, put it back the way it was before.
I don't know how it was. I made it.
Yeah, you had multiplied this times that for your last one here.
Yeah, I meant to do the other.
I know you did.
What?
I know you did. But just put it back so I want to. Oh, did you?
Yeah.
Oh yeah. Okay. So can you blow it up a little so we can see the numbers? Yeah. Okay. So as you guys know, you have been working on your ANOVA homework. And in the last 24 hours, I've been inundated with lots of questions from lots of people. One of the nice things about me interacting with Rachel is she's got her thing on a SharePoint thing so that I can actually just log on. Like when I was emailing back and forth with you today, Claire was in my office. I would help Claire, then I would look at your spreadsheet and I could actually see you working on your spreadsheet, which was kind of nice. But one of the reasons that I have you do these problems by hand, and even if you're doing it on Excel, you're not relying on any of the statistical properties that are built into Excel. You're actually typing in what the formulas are to get Excel to do the work that you would normally be doing on a calculator. And so what you're demonstrating for me is you're demonstrating that you know how the analysis operates. And so one of the reasons that I do this is because I want you to develop some degree of intuition about the numbers that you're working with and the analyses that you're working with. So Rachel and I have been going back and forth. She sent me her assignment and asked me to kind of look over it, and I looked at her last problem. I'm like, oh, your last problem, there's something wrong with it. So then I started plunking around, highlighting her different cells to try and figure out what was going wrong, where something was going wrong. And the first thing that I do when I get to a student's problem, the first thing that I look at is I look at their ANOVA table and see if their ANOVA table matches my ANOVA table. So I'll begin with the F statistic, work backward to the mean squared, work back to the sums of squares, both for the group and within, trying to work backwards through the problem to detect where the issue came from, why the student's analysis isn't matching what I thought the analysis should be. And so when I looked at this, what jumps out at you about this ANOVA table that should make you really pause at the very beginning? Yeah.
The F statistic's huge.
The F statistic is huge. Now you can have huge F statistics, and I've seen plenty of huge F statistics in my life, but that is pretty huge. What else in the ANOVA table should signal to you that something is not quite right? P-value is 0 because the F statistic is really huge. Yeah, so that's all part of the plan. But the F statistic is huge because mean squared group is huge, and mean squared group is huge because sum squared group is huge also. Why would we expect sums of squares of group to not generally be very big?
Yeah. Just less just adding less stuff up, I guess.
It's just adding fewer things up.
Yeah.
In this case, you have three different groups. Flex time, staggered starting hours, and fixed hours. So you're only adding 3 things together. And because you're only adding 3 things together, generally your sum squares treatment, or sum squares among, however you want to call it, that's going to be relatively small relative to sum squares within, because for sum squares within, you're adding up everything in the entire data set. And so whenever I see really big measures of sum squares within, sum squares among, I begin to think, oh, there's something wrong in the calculation of sum squares among. So then I go to the sum squares among, and I click on these things, and I see that they're referencing this cell. When I look at that cell, what does my intuition tell me about the grand mean? This is the grand mean.
That's not the grand mean.
It's not the grand mean. Why is it not the grand mean? Rachel?
Because it's lower than all the other.
It's lower than all the other means. So your grand mean should always fall somewhere within the range of your other means. So as soon as I got to that cell, I'm like, that cell's the problem. Because earlier, in an earlier iteration of it, it was way higher than the range of means that were the components of the grand mean. And in this case, it was slightly lower. You should always expect to see your grand mean somewhere within the range of the means that you're observing. So you yourselves can troubleshoot many of the things that are going wrong. Over the course of the last couple of days, many of you have sent me emails saying, there's something wrong with my answer to this particular problem in the problem set. I'm not sure what it is that is going wrong. Some of you, in some cases, actually identified what was going wrong, and that's good. That shows that you are developing your intuition. So click on this so that we can see the formula. Click up here so we can see the color. Yeah. So when I saw this, I'm like, why are standard deviations in here? Well, it's because instead of doing these two things multiplied times one another, she did these two things multiplied times one another. As soon as you fix that, what happens, Rachel? $31.59. That is what the grand mean should be. And once again, you see that grand mean is totally embedded right within here. But you see that there's this 35.3 that should be pulling that grand mean up. Why is that grand mean closer to the staggered starting hours than it is to the other two means? Yeah?
So much bigger sample size.
So much bigger sample size. So sample size is influencing the grand mean, which is why we incorporate sample size into the grand mean. Yeah?
Also, wait, we didn't have to do a post hoc test, right? Because it didn't ask for one.
On this question, I did ask for one. It was the first one that I didn't ask for, isn't it?
No.
Oh, which one did I ask for?
You asked for it on the first two if it needs to be. And
Oh, okay, and then I didn't on this one. Yeah,
Yeah.
okay. That's fine. If you did it, that's fine. If you didn't do it, that's fine. In this case, Rachel did do it, and so she got good practice doing post hoc tests. So now that this is the correct grand mean, what's happened to the sum squares within?
Much lower.
It's much lower. It's a much more reasonable, much more believable sum squares within. The reason sum squares within is so huge is because it's based on a huge sample size, such that when we divide that by the sample size, by the degrees of freedom, that mean squared within goes way down. Because we're dividing the sum squares divided by a fewer number of degrees of freedom, it goes down, but it doesn't go down nearly as much. And you end up getting what looks like a much more reasonable F statistic. As a result of that, this F statistic isn't close to 0. It's actually closer to 0.02, something like that, 0.019 or something like that. So for all of you, try and develop your intuition about the numbers that you are working with. It's coming along. One of the purposes of doing these exercises is so that you develop that intuition. There are tons of times when I'll do an analysis and I'll get the results and I'm like, that just ain't right. And at that moment, I can't identify what's gone wrong with the analysis, but after having looked at the data, doing some preliminary visualizations of the data and things like that, I look at the result and I'm like, all right, I screwed something up in there somewhere. I wrote a line of R code wrong or something like that. You should always be thinking critically about the numbers at every step through the process, because that's how you catch errors. And you guys have been catching errors on a constant basis as you've been going through this, and that's good. You'll get better at that as you go along. When I'm doing things by hand, I generally stop at every step along the way and say, okay, does this set of data that I've generated, does these set of numbers that I've generated, do those kind of match up with what my intuition tells me about what this data set is about? So now I think that's absolutely correct. Say that, Rachel, and submit. So the other thing that a number of you have asked me about is the post hoc test, because I think it's on the golf ball example. Is it the golf ball example? The golf ball example, I asked you to do post hoc tests.
Oh, no.
Okay.
You asked it on the first two.
Only do it if like.
Yeah, so
different.
what was
You
the
asked,
first
you
one?
asked for it on the first two. The first one didn't need one, the second one was the only one that needed one.
Second one was the one that needed one, and when you did it, what did you find?
Pretty much all were different, except for one.
Is that the case? Now I'm losing my mind.
Okay.
I've looked at so many different iterations of all the different questions. What was the question we were talking about there?
The one where we didn't have to do it.
Which one was that? Was that the golf
That was
ball?
our third question.
This
You
is the
didn't
third-
ask us, but I
Third
did
question.
do it,
Okay.
which was the golf ball.
Oh yeah. So in the third question, which is the golf ball question, I didn't ask you to do post hoc tests. And I guess the reason that I didn't ask you to do post hoc tests on it is probably because I knew from previous semesters that this is what was gonna happen. On the golf ball example, somebody tell me what they found for your F value and the associated P value. Yeah.
My F value's on my Excel, but my P value was 0.042414.
Okay, I got 0.043, that's probably just random. Brandon, what was the F?
3.529.
This look familiar to everyone? I don't have mine open.
Yep.
So if you did do post hoc tests on this, so we have three brands, we have golf ball brand A, golf ball brand B, and golf ball brand C. What you would have found had you done the post hoc tests on this is you would have found that when you compare A to B, there's no significant difference. When you compare B to C, there's no significant difference. And when you compare A to C, there's also no significant difference. None of the differences between the means exceed the minimum significant difference for the Tukey-Kramer test. And the reason for this is that what the ANOVA is testing is there an overall effect of brand of ball on the number of strikes that it takes to finally cause the ball to fail? So this is basically saying there is an effect of brand. So we know that there are differences in there somewhere, but it's a really small difference because this p-value is not very far from our critical value of 0.05. And so even if there is a difference, the difference isn't particularly large. Then we go and we run a Tukey's test, and we find that for each of these comparisons, each of these pairwise comparisons, we find that none of them exceed the minimum significant difference, something Rachel pointed out and asked me about the other day. You know, why do we not see any differences between any of the treatments, any of the brands, when we saw an overall significant p-value? And it's because when we do a post hoc test, the only reason we're looking at our data further is because the ANOVA has told us that there might be something different in there. So we've kind of used up part of the information that we have available to us, and tests like Tukey's test try and take that after the fact look into account. And so they tend to be relatively conservative, such that they don't want to reveal differences that might just be spurious, that might not actually be real. So Tukey's test takes a reasonably conservative, there are certainly more conservative tests, but as a result of it, it makes it a little harder to see differences after the fact. And so oftentimes when you see a p-value that is very close to the rejection criterion, you will sometimes see that when you go and look at all pairwise comparisons, you find that there aren't any individual pairwise comparisons that are actually different under Tukey's. And so what you say is that there's no effective brand, but you can't say which brand is higher than which other brand, for example.
So you say there is an effective brand?
There is an effective brand, but you can't discern, based on Tukey's test, which brands are different from one another. You can get an inkling because in one case, the minimum significant difference was 32 point something and the actual difference was 33. I think it was between A and B, wasn't it? And so this is probably the difference that the overall ANOVA is detecting, but under Tukey's it turns out that it's not actually statistically significant. So I was trying to think of a way to describe this, and this is something that we won't cover in this class because it's a more of an advanced topic. But you can use analysis of variance to do something called trend analysis. So the example that I used this morning was imagine that we have housing prices. So you're an economist and you're looking at the cost of housing, the sales, the amount that new home sales are going for. And so you have quarter one from 2019, quarter two, quarter three, quarter four. You have quarter one of 2020, quarter two, quarter three, quarter four, quarter one of 2021, etc. And what you notice is that housing prices are variable because housing prices are just variable. That's one of the natures of that particular data set. And what you find is that over time, housing prices have been increasing. And if you put this into an analysis of variance where quarter is your kind of treatment effect, what this analysis would reveal to you, because you have so many quarters of data, which means you have a lot of power to detect the effect of quarter, the effect of time in this data set, is that you will see that your overall ANOVA would be significant. And the reason for this is that the quarters are different and they're different in a systematic sort of way. And this is what trend analysis actually detects. But when you compare the first quarter of 2019 to the second quarter, are those different? They're not. First quarter and third quarter, not different. First quarter and the first quarter of 2020, they're not different. And if I had drawn my error bars a little carefully, the first quarter here and the last quarter isn't significantly different. But is there an overall effect of time, which is the x-axis in this case? Is there an overall effect of time? Yes, there is, and this is what trend analysis, which is based on ANOVA, detects. But you can have an overall significant effect of the x-axis, this categorical data, quarter one, quarter two, quarter three, quarter four, without having any of the pairwise comparisons being significant because there is a significant trend in the data. And so don't be surprised if you sometimes find marginally significant overall ANOVAs that then show no significance in the pairwise comparisons. I introduced you a little bit to Zach White's data, where we have all these different populations. One of his analysis of variance looks at body size in these lizards that he's working with. And we find that there's a significant effect of population. The populations do vary in terms of their body size, but when we run a two-piece test on it and compare all populations to one another, we actually find that none of those pairwise comparisons is significant because, once again, his significance level on the overall ANOVA was 0.04. And he had the same question. I mean, he doesn't have the benefit of being in this class, but he had the same question. How can none of the populations be different from one another, but the overall ANOVA is significant? I'm like, well, because that's the nature of the beast. The lower your p-value is, the more likely you're going to observe more and more pairwise comparisons that are significantly different from one another. So don't worry about that. Certainly, when you get that, ask yourself, why the heck did that happen? Because that seems like an aberration. Engage your statistical intuition about that, but then interrogate it and try and get at the root cause of what it is. Is it that I've done something wrong, or is it just that I had an overall ANOVA that wasn't terribly significant, and as a result, when I look at the pairwise comparisons, I don't find any pairwise comparisons that are significant. So, that said, are there any other questions about homework? All right, cool. Thanks for sharing your stuff with us. not pick anyone at random. I'm going to pick someone specific. Claire, you're on a Mac, aren't you?
Yes.
Can you put your screen up? I'm going to pick on Claire because we worked on this earlier today in my office. And she, I probably suspect, knows what's coming. I didn't tell her what was coming, but I suspect she knows. So everybody pull up your R script that we've been working on and get that run down to the point that we were at, because that's where we're going to start. What did I ask you guys to do as homework for today?
Take the data from this
Yep.
and make a significant graphic of it.
Yes, make an informative graphic. So Claire, make your text a little bigger. I think it's Control plus, Command plus. Yeah, there you go. So just so we can see what you're doing. Yeah. And then make your window over here just a tad bigger. All right, explain to us what you did. So we had run an analysis of variance. We found that the analysis of variance was significant. We haven't done post hoc tests, but a lot of times after I see a significant ANOVA, I kind of want to look at the data and see what the data are showing me. So explain to us what you did, starting with up here, actually. Go up a little. Yeah. Okay, so stop there. So she's using summary SE. Highlight just the summary SE part of this line and run it all the way down to treatment. Yep, just run that. So when you just run that, it will give you the output down here. And the output is the treatments, the sample size of each of those treatments, the variable, the mean of the variable of interest, standard deviation, standard error, confidence interval. But what she did was she did summary SE of the data in DAT. Measured variable was, in this case, treatment. No, measured variable was not treatment. Measured variable was transdat. And the group variable was treatment. But what she did was she assigned that to a name. Why do we use the assignment operator to take this long, complicated thing and put it under a shorthand tag? It's easier to reference back to if you ever need that, but also it stores the output. It stores that thing. Whenever you type in CI_plot, it's going to run that line of code that follows it. And so whenever you type in that, go ahead and run that line of code. Yep. It just gives you the output. Do structure. Tell me what the structure is of CI plot. It's a data frame. It's a data frame. So you can do things to that data frame just like you can do things to any other data frame. It treats it just like data. In this case, the data has a set of vectors. One of the vectors is transdat, which is the average value of transdat. One of these vectors is confidence interval, which is the confidence interval for each of those treatments. So now what did you do next? Yep, that's the data frame. What does AES stand for? It does stand for aesthetic. Yep. It's the aesthetics statement. It's telling you what is the x-axis. In this case, it's treatment. What is the y-axis? It's transdat, because that'll be the means. Why do you have y-min and y-max here? Okay, so she's putting in the aesthetic statement y-min, which is the minimum value, and y-max, which is the maximum value. And because she's wanting to plot confidence intervals, she's assigning that to the mean minus the confidence interval and the mean plus the confidence interval. Continue. She's got a plus at the end of the line here so that it continues relating things. So this is all. Actually, I think we're missing parentheses at the back here. Yeah, I think so. Oh, no, we're not. Never mind. Get rid of that. So we've got a plus that takes us to the next line. What is geom error bar? Okay, it's just going to plot the bars on the top and bottom. And then what is geom point doing? It's plotting the means. Yep, it's plotting the points, whatever the y variable is. So you have points that represent the means, and you have error bars that represent the 95% confidence intervals. So this is the most basic of all of the graphs that you can create. Is that a particularly aesthetically pleasing graph? No, it's not, because we haven't done anything to modify any of these things. We haven't gotten rid of this background and things like this. So it's not the prettiest graph that we've ever seen, but it's functional and it gives us good, useful information. It tells us that the control is different than everybody else. Sucrose is different from the control, and these three things aren't different from one another, which is exactly what we already knew from kind of working through this in class. What's wonky about this graph? Somebody other than Claire. I've already picked on Claire enough today. Somebody other than Karis. He's been talking too much today already. Yeah, Rachel. This one? What's wrong? What do you think is wonky with that? It is completely on its own, but so is control completely on its own. In the original data, which treatment grew fastest? Control grew fastest, but in this graph it looks like control is growing slowest because it has the lowest value. These three treatments were the treatments that struggled the most to grow, yet they're at the top of the graph. Why is this the case? Yeah. Because it's transformed data, and the transformation kind of flipped it on its head, such that the group that is growing the fastest has the lowest value in the transformed data. The things that grew the slowest have the highest value in the transformed data. So while this graph is useful in that it gives you the means and it gives you the confidence intervals, it is not terribly useful because it is not intuitively obvious to the recipient of the graph which of these groups is growing fastest. And it's because we had to transform our data because we had a homogeneity of variances issue. Okay? So when you create a graphic, you want the graphic to be both informative in terms of illustrating things like means and confidence intervals, but you also want it to be informative in that you want it to be intuitively obvious to the recipient of the graph what the result is. And so how do we fix this? And we'll work on prettying up the graph later, but let's talk about how we go about dealing with this particular issue. Yeah, sure. And unfortunately, I think I left my cheat sheet in my office also. I was a little rushed for time this morning. I'll be right back. Okay. Okay. So let's actually. Oh, so before we get any further into this, basically back transforming the data to create a better graphic. A number of you said on your comment cards that the coding went fine, but in some cases you didn't understand exactly why the coding was being done the way it was being done. Whenever you have those questions as we're going through, certainly stop me, because sometimes I'm just in the zone down here and I'm like, okay, I'm coding things. It should make sense to you why the coding is done the way it is. If you're not understanding why the coding is being done the way it is, stop me and I will explain it. Some days I'm better at explaining you kind of item by item within a stretch of code what's going on. Other days I'm not, and I wasn't particularly good at that on Wednesday. But the other thing that you should do is after you leave here, you should annotate your code. So I sat down and did this. I was doing this earlier when you were walking in. I was finishing up portions of this. So one of the things that you will see, except that you can't see it because I'm not sharing, because I'm not thinking ahead. One of the things that you'll notice in all of my code is my code tends to be relatively annotated. So this is the live coding sessions that I've been doing. So I haven't been annotating it on the fly because I've been trying to get through it. But one of the things that you should do when you're doing this, when you have more time available to you as you're coding, when you write a line of code and it works for you, you should write down an explanation as to what that code is doing. And why it worked or why it didn't work or things like that. Because that then builds up this body of knowledge that you have as to how our scripting actually operates. So what I did this morning when I got in is I just started taking this live script that we've been working with and I've been adding annotations. So what does getWD do? Well, we already know that. We're pretty familiar with that, but it doesn't hurt to write out for somebody who might use your code. Well, what does getWD? Well, it gets your working directory. What is this doing? Well, it's reading in the data file, but then it's also saving it as an object dat. And so you might want to put objects, for example, in quotes in your comments. What does head do? Well, it looks at the first 6 lines, and because I was doing this morning, I haven't proofread it. Looks at the first 6 lines of the data frame. Tail looks at the last 6 lines of the data frame. Dat, it outputs the entire data frame to the console window. That's not particularly useful, so you might instead want to do view, which opens the data frame in a new tab. What does structure do? It shows you the structure of the data frame. What does class do? It gives you the data type for the column labeled treatment in the data frame dat. Then I have this section that is called force R to keep variables in order. So what is this doing? Well, the first thing that it's doing is I learned from structure that it was treating treatment as character data, and I want it to treat it as factor data. So the first thing I'm going to do is I'm going to first set the column as a factor, which is what this line of code does. I'm going to use class to check and see if it actually did that. Then I'm going to look at the order, and when I look at the order, I see that the order has been rearranged from the original data file. Well, I want the order to be retained, so I have a little explanation here as to what exactly this is doing. This just tells R to take the factor levels as they appear in the order in which they appear from the original data frame. Then I go and check that again, and I see that the order is now the order that I want it to be in. So
setting up a model. So literally what this model says is it says first, create a new object and call it analysis. That's what the assignment operator does. Analysis is just shorthand for doing an ANOVA. That's what the AOV is. On growth, as it is affected by, that's kind of what the tilde means, growth as it is affected by treatment, and use the data in the data frame dat. That's a literal translation, a literal verbal description of what this line of code does. Make something new, call it analysis. It's an analysis of variance, growth as it is affected by treatment, using data in this data frame. So just write out literal translations of what the line of code is. That's how you develop your ability to write syntax in coding. I don't know if in the other classes that you've had in your data science you do this kind of transliteration of what lines of code are doing, but it's useful because it takes what seems like archaic code and puts it into plain English for you. So my advice is, as you're going through doing your scripting on your own, pause at the end of every line to define what's being done in that line. In live coding, we're moving faster, so you maybe can't do that, but as soon after classes you can go through and annotate your code so that by the next class period, you can have a reference as to what that code is actually doing. And as you can see, I only got this far. Because the rest of my code is totally unannotated because I didn't have time to do that this morning. So I need to unfortunately run this whole thing. So I'm just gonna knit the whole damn thing. Oh crud. I'm working with somebody on a bioinformatics project, and we ended up reloading R yesterday, and now it's going to take a few minutes for everything to extract. Oh, so you guys are like, why do I have you working in R Markdown? Well, because in R Markdown, what it gives you is it gives you a nice output where you see blocks of code, and then you can see the output from that block of code, a block of code, and the output from that block of code, a block of code, and an output from that block of code. When we get down to doing the ANOVA, when we run the analysis, there's the ANOVA table right there. I can just see that you ran an analysis of variance, and this is what you got as a result of it. So there's the histogram. And it's all in an HTML file, and I can just look at the HTML file and see what you've done, and then also see what the result of it is. I don't have to download your R script and your data file in order to see if your code is running. I will see in your R Markdown file whether or not your code is running appropriately. So let's just, let me get caught up to where you guys are at. Okay, so here's where we were. We did summary SE to get the summary output for this whole thing. And once again, the problem with this, as we've seen, is that this is transformed data, and as a result, it doesn't look particularly intuitive. So let's make a graph of the original data untransformed so we can see kind of what we're shooting for in a graphic. And one of the nice things about this is we're going to make this graph, and then we're going to actually be able to use that graphics code to make a new graph later on that will actually be the back transformed data. So The first thing that we're going to want to do is we're going to want to save an object. I use CIplot because it's a confidence interval plot, and use the assignment operator to then run summary SE on the data frame, but in this case, the measure variable is going to be growth, and the grouping variable will be treatment. I saw a hand up. Yeah.
Wait, so CI plot is an actual thing?
No, it's just a name.
Oh, okay.
I could have called it. My wife codes in R. She calls everything X just to keep things simple.
Oh.
So you could have called it X.
I was wondering because you said CI plot is a confidence interval because we're making a confidence interval.
I use CIplot because I'm using this to make a confidence interval plot. If I was making a bar graph, I might call it something different. But you can call it X just as easily.
Okay.
Do you mean to put summary W?
No, I'm a terrible typist. You guys should know that about me by now. Why is R not? Oh, I know why R is not cooperating with me. No, I'm a terrible typist in so many ways. All right, so when we do this, you can just type X, and what you see when you type X is that everything is now expressed in the original growth increments. Control grew 70 millimeters or whatever. Glucose grew 59, fructose grew 58, 58 and 64. This is the ordering, this is the magnitude of the growth in the actual directions that it is. So now that we have that, done, let's make a couple of little notations. So now what we can do is we can make a new plot. I'm going to just call this plot OGraph, and once again, I'm going to use the assignment operator. And what I want to do is I want to invoke Ggplot, and in this, it tells you once again, kind of up at the top, it'll give you a little yellow box that tells you what you need to have. So you need to have the data frame. In this case, the data frame for me is X, because Keras made me deviate from my normal behavior. And then we're going to have an aesthetics statement. In this case, the X variable is going to be what? Treatment. Good. The Y variable is going to be growth in this case, because we're working with the untransformed data. We can go ahead and set the Y min and Y max for our confidence intervals. So Y min is going to be growth minus the confidence interval. Y max is going to be growth plus the confidence interval. Now, if we want to see what this graph looks like, we have to invoke it. We have to call it up. So run this first line, and it should just give you a return of the command prompt in the lower left-hand side. But then run the next line and ask it to give you the graph. And what you see is it's given you a box. And it's a bare box because you've told it what the treatments are: control 2% glucose, 2% fructose, 1-to-1, and sucrose. And you've told it that the Y variable is growth, but what have you not given it? You haven't given it what to put in the box. So you need to tell it what you want to have it put in the box. So at the end of this first line, put a plus. And then what you want it to put in the box is you want it to put points. And for now, we'll just do an open parentheses. This should be geom. All of these are geom, standing for geometry. Geom point. If you just run that, and then get it to output it, you now have a graph that has points on it because you've told it something to add to the graph. But is that all we want? No, we also want error bars, so we need geom underscore error bar. And when we do that, it gives us these really ugly error bars that are really, really wide. And so we can actually go in here and we can do something like width equals 0.2. And that makes error bars that are a little prettier. Put up your green tab or your blue tab if you've gotten that far. Yeah, what do you got? Oh, okay. Is that the first error that you got? I've never seen Ggplot add. Oh, you've got a plus at the end there. Now do it. Yeah, now do it. Now call it up. Yeah, there you go. Don't ever end a line in a Ggplot thing with a plus, because then it's expecting something to come after it. Yep, that's a common enough mistake to make. So now we've got a plot that is a little prettier than the plot that we had before, because it doesn't have these weird wide lines at the caps. You can set this to whatever you want, and depending on what you're doing, you might want them to be smaller, bigger. Just, I'm all about proportionality. What else might we want to add to this or subtract from this in order to improve the appearance and utility of this graph?
With more, like, I guess more detail and more precise scale on the y-axis.
Okay, so we might want to do that. I don't usually do that very often. Let me see if I can think of scale y. Continuous breaks. Okay, scale y continuous. So I'm using tab complete. So scale y continuous basically is how you can alter the characteristics of the y-axis. There's also scale x discrete, because in this case our x variable is discrete, and so we can customize this. Yes, ma'am. Okay, so you have to now put a plus in there so that it outside the parentheses. That tells it to go to the next line. Yeah, so you need pluses within, but not pluses at the end. So yeah, the plus, you could actually write this all out in one long line. I give myself returns so that it fits kind of within the window that I'm working in. But basically, the aesthetics statement is one thing, the geom point is another thing, geom error bar is another thing. And so anytime you move from one thing to the next thing to the next thing, you have to link them with pluses. But if you get to the last line of your graphing block and put a plus there, it's expecting for something else to be after that plus. So you have to put pluses in the middle of your different things that you're asking the plot to make, but you need to leave no plus at the end, because that signifies to R that you're at the end of creating that graph. So I don't remember how exactly breaks works, but let's see if we can get some. Let's run that and see what it did. Whoa, it did not do anything. It got rid of everything. Ah. Let's see what that does. Well, once again, I don't use, so you can basically tell it whatever breaks you want it to have, and it will put those in there. I missed 61 because I'm a dope. You can also do something, once again, I don't usually deviate from the defaults very much. Yeah, okay. Yeah, so you could certainly do that. It would take me a few minutes to figure out. You can actually tell it to set a range and then tell it to break it up into set numbers, a set width of increment. But once again, I don't mess with that often enough for me to have that actually scripting on the top of my head. But you can certainly do that. So you can have it do whatever it is that you want. And this is no different than the default. It was just me defining then what it is. And
Sorry.
yeah,
I was just gonna say, if you go, I just tried something out.
Yeah.
If you go 0:100, for x equals 0:100, it looks pretty good, I think.
oh yeah, okay. So that gives you, oh yeah, it's breaking it up by ones. Yeah, okay. So it's basically saying you're breaking it up into anything between 0 and 100, and the default is just 1 unit increments. So you did you look that up somewhere?
No,
No,
I just
yes,
tried.
okay. Yeah, that's sometimes a good enough thing to do. So it's reverting to a default, and you're just telling it a range of numbers to do it across. All right, what else might we want to do to pretty this up? What else do you not like about this graphic? Is this a graphic you would want to turn into me? You can, but there's not really any reason to do that because there's only one axis of variation. That's more useful when you have two axes when we're doing a two-way ANOVA, but yeah, you could do that. Would you normally capitalize growth? And you need what? Oh, it might be nice to have a header also. Okay, a title. Okay, so thing called GG title, and you can just type in what the title is. So what is this? This is and it gives you a title. What else might you want to have? You might want to actually force the y-axis to have a label. ylab turns out to be the code for that, and once again, you can just put in whatever you want and just put it in quotes, and it will just type exactly what you want it to type. So in this case now, It not only tells you what it is, but it also has the units that it is in, and it's now capitalized where it wasn't capitalized before. What else might you want to do? Oh yeah, you can capitalize treatment, so that's the X label. And so, and I forgot to put it in quotes, but you can do that as well. Once again, we're just building up a graph piece by piece, finding things we don't like about it, figuring out what it is that we have to do about that thing that we don't like about it, and then doing that. And so building up a graph incrementally this way is useful because it gives you experience with what exactly all the capabilities of ggplot are. There will come a point where you'll get familiar with what you like your graphs to look like, and then you'll just know to put these things in there from the very beginning. You won't have to build it up in this way, but this is not a bad way to start. What else is irritating you about this graph?
Is there any way to space out our treatments so we can see them clear?
Yeah, for now we can do that. One way to do that is to just make the graph a little bit bigger, because ultimately we're going to export. Go up here to the Export tab, and you can save this as a PDF. And for example, you can put this on an 8.5 by 11 sheet of paper.
Wait, where is that?
Oh yeah, sorry, I moved too fast. Export. It's right here in the graphics pane. Click on Export. You can either save it as an image or save it as a PDF. I generally find PDFs are more scalable when you get them into another application, like a Word file or something like that. So you can save it as this, and when you do this, you can click View Plot after saving, and if that's checked, it'll just show you what the plot looks like. You will see in an actual output of it, it ends up not being overlapped like that. That's just a factor of how small your window is. But one of the things that you do notice is that these things are really, really small. And so they're a little hard to read. So one of the things I always like to do is I like to look at my graphic the way it's going to finally be output and see if I need to change anything, for example, about the sizes of fonts and things like this. So what do you not like about this graph the way it's looking at this point? Now that you can see it in a kind of an output form. Oh, really? I feel like this graph irritates the crap out of me. You would want it in the middle, wouldn't you? Why is it stuck over there on the edge? Well, because sometime about 2 years ago, somebody changed ggplot so that it left justifies the title rather than centering it. Well, that's something that we can actually change. It would be nice if the title was centered and bigger. It would be nice if the y-axis label and the y-axis numbers were bigger so you could actually read them better. It would be nice if the treatment labels were bigger. What else is irritating about the treatment levels? They're small, so it might be nice to increase their fonts. What else is wrong with them? They're all, we already fixed it about the labels. They're all lowercase, and generally you wouldn't label things with lowercase. We do things in lowercase in R because uppercase is just difficult, because then you have to remember what's uppercase all the time, because R is case specific. So let's just go and fix all these things. So to fix the label on the x-axis, we use scale x discrete, because this is a discrete axis because it has discrete categories. And what we want to do is we want to change the labels about this, and we want to just give it a list of labels. And so C is just combining the things that come after it. So we want to do a label for control. Then we want to do a label for 2% glucose, except that needs to be in quotes. Then we want to do 2% fructose. Then we want to do 1% glucose to 1% fructose, and then we want 2% sucrose. But one of the purposes was to capitalize, and I didn't capitalize. When we do that, we've changed the labels. How do we change things about the aspects of the axes and the titles and things like this? We generally do this through theme statements. And so type in the word theme, and I'm going to just give you some preferences that I have. I tend to like my figures in black and white. Whoa, sorry. So theme underscore black and white, you can just do by itself. Then there are things that you can do with every aspect of the figure. So let's start with plot title. I told you I was the worst typist on the planet. So plot title, sorry, that's a dot. Plot dot title.
So what is this theme doing?
It's just changing aspects of the graph. So now we're about to start messing with the plot title. So theme is just thematic elements of the thing. What's going on with the title, what's going on with the axis labels, what's going on with the axis ticks, et cetera, et cetera. Yeah. Yes, we can do that also. Right, now you're throwing a lot at me all at once. So let's do theme black and white. So let's now do theme panel dot grid major equals element underscore blank comma panel grid, in this case let's do minor equals, and do the same thing. Now run that whole thing, and you've gotten rid of all that junk in the background. Okay? So, homework for Monday. Think about this graph. Think about what you want to change about this graph. See if you can find some solutions on how to change this. Save your work from today. On your tabs, write down what went well today. Write down what didn't go well today. I do pay attention to those things.